Okay, hello everyone. This is actually the last set of notes for this semester, video notes that you'll have. What I will advise you to do, because sort of a lot that I wanted to cover because I wanted to finish everything. So I wrote mostly everything down ahead of time. So when I go to each slide, you may want to just pause the video, write everything down, and then play it. So it'll make more sense. And so you could do that now. So this is section 5.2, which is still dealing with infinite sets. And the presentation actually talked about some of the things that I'm going to talk about, but I wanted to reiterate it and just make sure. So I'm not going to go over the examples that they did, but I just wanted to reiterate some of the things that they talked about in this section. So notice that you have additional homework problems. So that's what you'll be working on in class tomorrow. And okay, we're just going to get started. So I wanted to look at an example. I don't believe they showed this one, but we're just going to look at it quickly anyway. So P is the set 1 over 2 to the K, where K belongs to the natural. So that's 1/2, 1/4, 1/8, and so on. And so this is a bijection between the naturals and P. And the bijection is given by, this is a straightforward bijection, or in terms of its function. So H goes from the naturals to P, given by H of n equals 1 over 2 to the n. Some functions, so some sets sort of lead you straight to what your function should be, and you can clearly see that it's onto the naturals and others may not. What I will say is, because this is still Foundations of Mathematics course, and because I want to make sure you're still learning, not learning, you learned on the proof techniques, but I want to make sure your proof structures are strengthened. I would advise you to show that bijection, if in terms of saying, well, it's clearly a bijection. When you get in more advanced classes, you could probably just say that. But in our class, I still want you to show that bijection, and it's the good practice, right? So show it's 1-to-1 and show it's onto. Okay, so I am going to leave you to do that. So I want you to show that that's a bijection between the naturals and P. All right, and you're given the function already. As you saw in class today, sometimes you're not given the function. All right, so you're going to show H is a bijection, and then once you show those steps, show it's 1-to-1, show it's onto, then you can say, I just want to be clear on a little bit. It has a little structure in the sense that you would say, well, showing that it is a 1-to-1 correspondence with the naturals is showing that it's denumerable. But we know that denumerable sets are infinite. So you would say, thus P is denumerable, and therefore P is infinite. Okay. All right, now here are some theorems. Again, in this section, besides proving bijections and developing your own functions, but besides proving bijections, I'm really not looking for you all to actually understand how to do these proofs of these theorems. I'm not, because like I said before, it took hundreds and hundreds of years for mathematicians to really think about it. And this was before television, so they had time on their hands and reality shows did not exist. So they really had time to think critically about things. Okay. So here, theorem 5.2.3. So this, I'm showing this theorem. The proofs in the book, I believe, it's short. It's not too extensive. But I'm showing you this because this may come in handy when you're doing your homework. So the set n cross n, so that's the natural cross naturals, is denumerable. And if A and B are denumerable sets, then A cross B is denumerable as well. So just keep those theorems in mind. You may find it useful for the homework. Okay, so now let's look at some more definitions. So a set S is countable if and only if S is finite, and a set is finite if it's the empty set or if it's equivalent to n sub k, right? Or denumerable. I'm going back to the definition, so I don't want to confuse you. So a set S is countable if and only if S is finite or it's denumerable. Okay, and S is uncountable if it is not countable. Okay. Okay, so this was the diagram that the presenter showed you. It's in your book, figure 5.22. And so just to clarify, we have the denumerable sets are in the intersection of finite sets and uncountable sets. And so, the intersection of countable sets and infinite sets, because a denumerable set is both countable and it's infinite. Okay. And so countable sets are finite sets. Countable sets are just sets you can count. Now, it might take you the rest of your life to count them if it's the natural numbers, for instance, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You don't want to hear Dr. Bourne going on forever. I don't want to hear myself going on forever, but it's countable, right? So that's why denumerable sets are countable, because it's equivalent to the natural numbers, and finite sets are countable because they stop, right? And it's really interesting because you guys are really in a high, in this high level class, but the whole notion of finite sets and countable is really elementary school, right? Because if you have some blocks and you place some blocks, and for a child who's learning to count, they actually create a 1-to-1 correspondence. You ask them, well, how many blocks are there? And they'll say 1, 2, 3, right? So that's creating that 1-to-1 correspondence. So it's really countable sets, and the notion of this is really elementary, but to really understand it takes a critical mind, and that's why you guys are in this class doing this. Okay. So when it's non-empty, so my note here is actually just for countable sets. And just again to reiterate, so when it's non-empty, there's this bijection. So when we're talking about countable sets and proving that sets are countable sets, we're setting up a bijection, and just depending upon if it's a finite set or numerable set, we might be setting up our bijections differently. So that's what I have here. So if it's a finite set, then we're setting up a bijection with n sub k. Okay, because it stops, right? So it's 1, 2, 3, all the way up to k. But if it's a denumerable set, we're showing that we have a 1-to-1 correspondence or a bijection with the natural number. So you go on forever, but you can count it. It's countable. Okay. And so an important definition, and you might hear it in other courses, is that denumerable sets are both infinite and countable, right? Because they're in that intersection. Right over here. And so they are called countably infinite. Okay, so denumerable sets are countably infinite. Countably. And it almost sounds like an oxymoron, right? Like the bittersweet. But no, it's countably infinite. So it actually exists. And now you guys are able to explain what that means, if anyone should ask. Okay. So since we now understand countable sets, we have an idea. We understand countable sets. We know what it means to prove a set is finite. A countable set is either finite or denumerable. We know how to prove that. But what about uncountable? And so here, the real numbers is actually uncountable. And if you think about it, it makes sense, right? Because, let's just talk about the interval. The interval 0, 1 is uncountable. And if you remember that there are an infinite number of values between 0 and 1, right? And so before we prove this, we have to get some more information and do a definition. So here's a note. Any real number can be written as any real number in the interval 0, 1, okay, can be written as 0.a sub 1, a sub 2, a sub 3, a sub 4. These are just indices where each a sub I is an integer between 0 and 9. Okay, and that makes sense, right? So, for example, and this is from the book. I'm just sort of highlighting what they talked about. So 7 twelves is equal to 0.58333, which equals to 0.583 repeating, right? So that's what I mean. So in that instance, then this right here will represent a sub 1, this would represent a sub 2, a sub 3, and actually a sub 3 on to infinity, right, will be 3, right? So you always just have 3 for the rest of that, okay? So we know that. We have that fact that we can use. We're going to need to know that. And definition. So let's say, so x equals 0. A sub 1, a sub 2, a sub 3, dot, 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 is said to be in normalized form if and only if there is no k such that for all n belonging to k, a sub n equals 9. Okay, so here's what that means. If we had, and the book had, I think maybe gave you some more examples, but just for sake of time, if we had 0.50, that's repeating, that's normalized, but 0.49 repeating is not. So basically, your repeating number or your because we're talking about infinite, right? It's not going to be a final number, but you're repeating, so that repeating number or that so-called final in the sense that this n greater than k is that there's always going to be an n greater than k, right? There's always going to be another number when we're talking about a number that's goes irrational number in particular. We're talking about an irrational number that goes on, right? Goes on without a repeating pattern. But what we're saying is there's always going to be, if there's an n that's greater than another number, then it's no such k that a sub n equals 9, okay? I hope I didn't confuse you. I feel like I did because I feel like I confused myself. All right, but anyways, hopefully this example makes sense though, right? So 0.500, because that's 0.5 with zeros repeating. This is 0.49 with nines repeating. That's not normalized, okay? Because that 9 is on the end, okay? There's no such k. So again, this definition is saying no k such that for all n greater than k, a sub n is equaling 9. Okay, so 9 is not that last digit. Okay. All right, so here's a fact that every real number can be expressed uniquely in normalized form. And that's where mathematicians, we have different conventions on, okay, this is set in stone because things can be viewed different ways. An example of that is the purpose of order of operations. Because if order of operations didn't exist, then we could have different responses, different solutions to the same problem, where that's not what we're going for, right? So we're saying that if it's in normalized form, then we can express it uniquely. So although I just wanted to make a note, 1/2 is actually the same as 0.49 with the 9 repeating, which is also equal to 0.550 with the 0 repeating. Only 0.50 is normalized, okay, because it's not, that 9 isn't the last digit there, okay. There's another digit besides 9 there, and that's what normalized means. Okay, so here's theorem 5.2.4, which says the open interval 0, 1 is uncountable, okay. So again, it's really difficult to show something is uncountable when the definition is saying it's not countable, right? So since we know we're trying to show it's not countable, then we need to show that 0, 1 is not finite and it's not denumerable, okay? Because that's showing that it's not countable. All right. So this first part right here, and I guess I should have put, so that's 1 and that's 2. 1 is going to be really short and sweet and quick. So since P, and that's why I showed you that set that we proved was infinite, notice that that's a proper subset of 0, 1. And you can think about the values to see that all the values in P are in 0, 1, the open interval 0, 1. So we show P is infinite. By theorem 5.16, 0, 1 is infinite. Okay, and feel free to go back to look at that theorem to make sure that makes sense. All right, if you have questions, please ask me in class tomorrow. All right, so we need to show that 0, 1 is not denumerable. And we're going to do this by contradiction, right? Because we don't know we know how to set up something if it's denumerable, or we know what it means when it's denumerable, but that means it's equivalent with the naturals, right? So suppose 0, 1 is denumerable. Hence, 0, 1 is equivalent to the naturals. That means we can set up a function from the naturals to 0, 1 that's a bijection, so it's 1 to 1 and onto. And we're actually going to show f fails the onto part. So sometimes when you're looking, so for this proof, showing that it fails the 1 to 1 isn't as clear, but showing onto, we're going to show it, although that's, when you see the proof, it's quite interesting, but hopefully you sort of understand what they did, okay? So we're going to show f fails the onto property, and what I did, and you can check to make sure this is correct, you can write what it means to be onto with our two sets and then take the negation of it. So this is actually the negation right here of the onto. So the negation would be there exists a y in 0, 1 for every x in the naturals such that f of x does not equal y. Okay, so, and this is actually good review for the final because you're going to have to negate quantifiers, all that stuff that we did at the beginning. You're going to need to remember that. So why don't you try and actually write out the onto quantifiers and then negate it to make sure that this is correct. Okay, so I think I have a couple more minutes left. We're almost done, so I'm just going to keep going on this video. The images of f, and now I'm using language that your book used to prove it, but the images of f, that's just your range, right? Because remember that, or your codomain, because this is onto, that means the codomain equals the range. So it's just 0, 1. So the images of 0, 1 of f for all n belonging to the naturals in normalized form is, and this is how, so we're going to represent it by, well, f of 1 is going to be point A11, A12, A13, dot, dot, dot. And we don't need to know what it is. Now, I'll tell you this because it might be clearer to see this proof with actual numbers in there. So tomorrow, if you want to see it, I can show you, or just remind me and I can show just an example of how this proof is sort of set up. Okay. Actually putting in numbers so you can see, or for yourself, just put in numbers and then try to follow the proof after you go over the proof first, and then you can go back to look at it. Okay, so f of 2, A21, A22, A23, dot, 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 f of 3, A31, A32, A33. Okay, again, this is indices to help keep us organized on how we want to set this up. Because again, we're trying to prove that it's a one-to-one correspondence, that it's onto the naturals, but we're going to show a contradiction because it's not, right? Because it's difficult. Think about setting up a one-to-one correspondence, kind of difficult to do that. Dot, 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 f of n, point a sub n1, n2, n3, and then it still goes on, right? Because we're going on forever with the naturals. Okay. Now here's where I haven't researched it yet, but I would assume it took mathematicians a minute to come to think of this part right here. Okay, so define B. B is going to equal 0. B sub 1, B sub 2, B sub 3, and B sub 4. And how we're defining it is that B sub I equals 5 if AII is not equal to 5, and 3 if AII equals 5. Okay, 5 and 3, these numbers here are arbitrary, okay? As long as you don't use 9, because using 9 might mess you up because of the whole normalized form, you can use any other digits that you want in there, okay? So those aren't, it's not a specific reason why. Now, how we set this up is interesting, right? Okay. So if we notice, if we do that, so what this is saying, so B sub 1, all this is saying is B sub 1, you go look at A11, right? So you look at this number, and if this number is a 5, then this term is going to be 3. But if this number is anything other than 5, then this number is going to be a 5, okay? And you do the same, B sub 2, you look at this f of 2, okay? So because of how we constructed it, so this digit right here is either going to be 0.5 or 0.3, right? And because of its construction, we know that B is going to belong into the interval 0, 1. So since B is an element in 0, 1, if we're claiming that this function is onto, that means there must exist an element in the natural numbers that's going to map to B, right? That's what that means. And this is where really understanding that the definitions of onto, one-to-one, and all the other definitions are really important. Okay, so then B belongs to that because of its construction. By our choice of B sub 1, though, f of 1 does not equal B sub 1. And by our choice of B sub 2, f of 2 cannot equal B sub 2. And this pattern goes on. This is actually, so if you notice what's happening, and this is something, I don't know if we're going to get to it, it's called diagonalization. It's a type of sort of proof, and I'm pretty sure you'll see it in other classes. But if you notice, B sub 1 is going to be dependent upon what A11 is. B sub 2 is going to be dependent upon A22. And The diagonalization goes like that. So you're picking up sort of in a way, you're looking at those digits in the diagonal to determine what your B is. And because you're looking at the numbers on the diagonal, there will never exist a B that's going to equal F of whatever your natural number is. Okay? All right. So thus, for every n in the naturals, F of n will never equal B, okay? And so this contradicts our assumption that F is on to 0, 1. Thus, 0, 1 is denumerable, and therefore 0, 1 is uncountable, okay? Definitely, I know you probably need to go back over that. It's interesting, but once you get it, it's quite beautiful, actually. Okay, let me go on. All right, so here's the last definition. This is the last slide, and so we're almost done. Definition, let S be a set. S has cardinal number C. So C here is not representing a variable in the sense of a variable. And I have the definition of what C is. It actually represents a number, a cardinal number. But we're talking about uncountable sets, so it's sort of different. If and only if S is equivalent to 0, 1, okay? And the notation, so the cardinality of S we say equals C, and C actually stands for continuum. And this is some really higher level math that we're getting into, and I'm excited I was able to share it with you all this semester because I did not get a chance to get to this last semester, okay? So this theorem just says 5.25, the set R is uncountable and has cardinal number C. Now there's two examples that I want you to go over, so make sure you look at the examples after this theorem, write them in your notes, and they're actually not too difficult because they're visual representation. They visually show you how a set is equivalent to 0, 1, the open interval 0, 1, and it's actually not too bad. So just look at those examples, and we are done. So we'll be working on the homework problems in class tomorrow.